Alright, so I'm making this video to pre-teach Chapter 8. We're talking about how to simplify when you have those square roots. So I'm just going to go through a few examples here to help you. There are notes. There's For your handout, there's a PDF that I posted on Classroom, so you can just fill in the blanks. But I just figured I'd go through the examples with the worksheet so you knew how to use it. So just starting with number one here, if I have a square root of 27 and I want to clean this up a little bit, I just need to break down that 27 into its pieces, into some factors, right? So I know that 27 is 3 times 9, right? And that 9 is 3 times 3. And I don't know. You guys might do a lot of different things for factoring. Like you might draw that factor tree, you might come up with all sorts of different things. But however you do it, when you break it down here and you get these three different threes, for every pair of any number that you have, you can pull that out. So this is a 3 root 3 answer because one of those threes has to stay, but the other two can be pulled out because you had two of them. It's a square root for a reason. As long as you have two things in there, you can pull them out. So then when I get to this root 50, right, I know that that's 2 times 25, and I know that the 25 is actually a 5 times 5. So I have two 5s, I can pull those out, and I'm going to have a 5 root 2. On this third example, root 72, so I'm just going to break this down bit by bit, and you can do it in any way that you want, right? 72 is, what, 8 times 9? So I could start with that if I wanted to, right? And I'm looking for perfect squares like 9, because 9 is going to have two 3s, and I can pull those out, right? The 8 itself has a 2 and a 4 in it. And a 4 is a perfect square because it's got two 2's, right? So I get to pull out a 2, I get to pull out a 3. That's going to be a 6, but I leave behind the root 2. That's going to be my answer. So again, however you want to break these down, it really doesn't matter. You guys should have some experience with this, but if not, we got practice right now. So the 120 is going to have what? And I can start simple. I can go 2 times 60, but then start breaking that 60 down. If I do it again, now I have two 2's, but then a 30. Can I get anything out of that 30? 30 is 6 times a 5. 6 is 2 times 3, but I don't get any pairs out of that, and I'm down to prime numbers, my 2, 2, 2, 3, 5, because the 6 got broken into two 3's, but can't do anything with those anyway, so I'm stuck with that 30, really. So it's going to be 2 root 30 as an answer for this fourth example. And then things get interesting because you have fractions sometimes. This fraction has two perfect squares in it, so I know right away that my answer is going to be a 2 over 3 because 4 is 2 times 2, 9 is 3 times 3. No more square root. But on 6, on this example, that 20 and 245, those are not perfect squares, but there might be perfect squares that are hiding, right? If I reduce this, right? Sometimes reducing is best. So both of these are divisible by 5. 20 divided by 5 is 4. 245 divided by 5 is actually 49, both of which are perfect squares. So I can get my 2 and 7 out, and that's my answer, right? But on number 7, I could reduce it, but I might have issues if I reduce it. It kind of depends, right? 9 is already a perfect square, so I know that's a 3 times 3. And on top, I have 24. I could make that like I can make it a 4 times 6, right? And I might write it that way because 4 is, again, another one of those perfect squares. I know that I can pull some 2's out, right? If you have to break it down further so you can see those two 2's, that's fine. The 6 has a 2 and a 3 in it. And again, the reason I could reduce it before is because both top and bottom are divisible by 3, and you can clearly see that now. But otherwise, if I reduce it before, I'd have to unreduce it after, because really, I get stuck. I need to pull out these 2's and these 3's. So I have 2 root 6 over 3. And the biggest thing about these fractions is you cannot end up with a square root on the bottom. You have to clean it up further than that. So like this next example, that 3 on the bottom is going to be a problem, right? I'm going to start out by breaking down the 28 as much as I can, right? A 28 is a 2 times a 2 times a 7. Now it's really a 4 times 7. That's how I would normally write it, but these are the prime factors of 28. And I can pull a 2 out, and that's great. But I'm still stuck with a 3 on the bottom, and I can't keep anything on the bottom that's a square root. So what I end up having to do is multiply the top and the bottom by a 3. Remember, you can always multiply the top times the bottom. And that's going to help me because now I have a pair of 3's down here and a pair of 2's, and I can actually pull those both out, leaving behind 7 times 3, 21 in my square root, but I do not have a square root in the denominator of my fraction, right? So when I clean these up, I have to get rid of that. That's just a rule. So again, on that last example, if I would have reduced it beforehand for number 7, let me switch colors here so you can see a difference. If I would have reduced it beforehand and turned it into a, what would it be, an 8 over 3. And I'm doing a square root of that, right? Oops, that was weird. So I'm square rooting 8 over 3. All that I'm going to get are 2 times 2 times 2 for the top, right? But that still leaves a 3 on the bottom. So I have to multiply by 3, top and bottom, which gives me exactly what I had before for my 24 and my 9. So I'd reduce it just to unreduce it, right? If you see a perfect square on the bottom, just keep it there, right? But otherwise, start breaking things down, reduce as much as you can, and you'll get an answer eventually, right? Then these last few, right, I already have that 5 out of this 5 root 12, so I'm just trying to pull out as much more as I can. That 12 is a 3 times a 4, right? Again, I know a 4 is 2 2's, so I can make this a 10 root 3, because it's 2 times 5 for that 10. Then I got 4 and 18 here. Again, I'm looking for perfect squares. This time 2 times 9. 9 is going to be what I need to pull out of here. So I get a 3 times 4 gives me 12 root 2. 11, I'm squaring what already has a square root in it, right? The square would normally just get rid of a square root, but in this case, it gets rid of the square root around the 5, but it does not. But it does affect the 2 as well. So I have to square the 2 and just remove that square root from the 5. So you end up with like 2 squared times 5, and that's going to be 4 times 5, which is actually 20, right? So make sure that you know how that works. I get rid of the square root, but I'm going to have to square that 3. So I'm going to have 9 times 7, 63 as an answer for this one. Again, lots of different ways to do this. This is just how I think about it. I've never actually really had to teach this subject to a class before, so maybe if you're getting lost, you go talk to Miss Heiser, right? But again, there's no real wrong way to do it as long as you end up with that simplified answer. Those last 4 examples are actually from the worksheet. I'm going to do another couple of videos to help you with those to make sure you get good answers. Otherwise, that's enough for this video.